Okay, today we are going to look at a classic example of integration using polar coordinates. Actually, double integration using polar coordinates. So we are going to find the area under this bell curve, z equals e to the negative x squared. And this is a curve that comes up often in statistics. And interestingly enough, we're going to start with a single variable indefinite integral of the function e to the negative x squared as x goes from negative infinity to infinity. So again, the integral represents the shaded area in the graph here. And while this is an improper integral, the function decays very rapidly as x moves away from the origin. Or in other words, the value of the function approaches 0 quickly as x approaches positive and negative infinity. And you can show that the integral converges. To evaluate this integral directly is very difficult, but a clever trick that some very clever mathematician came up with, not me obviously, can be used to evaluate the integral. Okay, the clever trick is to square both sides of this integral. So area squared, which I'm calling a squared, is going to equal the integral from negative infinity to infinity of e to the negative x squared dx squared. But instead of writing the right side as the square of an integral, I'm going to separate this into two separate integrals. So I'm going to have the integral from negative infinity to infinity of e to the negative x squared dx times the integral from negative infinity to infinity of e to the negative y squared dy. I've arbitrarily chosen to use y as my dummy variable. You can use any variable other than x and z, which are already being used in the problem. This is just a dummy variable. But the integral of z, or if z is equal to e to the negative y squared dy, is going to be have the same value as the integral of z if z equals e to the negative x squared dx. So these are equal and therefore equal to the square of the right side of our equation. Okay, this is by some version of Fubini's theorem, which we learned earlier. This is equal to the double integral over the entire xy plane, which is all of R2. The double integral over the entire xy plane of e to the negative x squared, e to the negative y squared dA. Now this is different than the version of Fubini's theorem that we talked about, because that was over that version was over a domain which was a bounded rectangle. And this is an improper integral over an unbounded domain. All of R2 is an unbounded domain. So in order to evaluate this integral, we need to be careful with our conversions. And I'll just repeat again, informally we know that this improper integral converges because e to the negative x squared times e to the negative y squared decays rapidly as x and y move away from the origin, as I mentioned earlier. That can be proven with more rigorous proof, but we're not going to do that right here. So what we are going to do is we are going to convert our double integral into polar coordinates. We can rewrite the integrand first as e to the negative x squared minus y squared, which will make doing that conversion easier. And we'll also convert the limits of our integrals to limits in terms of theta and r. And then it will be much easier to evaluate our double integral. Okay, so if you think about our domain as if x and y are included include all real numbers, then that means that our radius in polar coordinates can be anything from 0 to infinity, and theta includes all angles, which means theta will go from 0 to 2 pi. Also, using the polar conversion, x squared plus y squared is r squared. I know that negative x squared minus y squared must be negative r squared. So again, x squared plus y squared is r squared, then negative x squared minus y squared equals negative r squared. Okay, I am ready now to rewrite my double integral in polar coordinates. So I'm going to say that a squared equals the integral from where theta is 0 to where theta is 2 pi times the integral where r is 0 to r is infinity of e to the negative r squared r dr d theta. Where did this other r come from? Don't forget, that's our magnification factor. When you convert from Cartesian to polar coordinates, you wind up with an r, an additional r in your integral. And you can go back and look at the lecture introducing polar coordinates in double integrals to review where that r comes from. All right, it is time to integrate. So, this is going to be the integral from 0 to 2 pi of the, let's write this properly, this is going to be the limit as t approaches infinity of the integral from 0 to t of e to the negative r squared r dr d theta. And if I think of this as an e to the u du, if u is negative r squared, then du is negative 2r dr. So I'm going to put a negative 2 in here, so I have a du, and I'll balance that by putting a negative 1/2 out here. So now I can integrate this. A squared is the integral from 0 to 2 pi times the limit as t approaches infinity of negative 1/2, and e to the negative r squared negative 2r dr just becomes e to the negative r squared from 0 to t. Okay, I'm going to pull my negative 1/2 out to the front. A multiplier, a constant multiplier, can be taken out of the integral. And so what am I left with here? This is going to be the limit as t approaches infinity of e over t squared minus 1. Okay, e over t squared minus 1. D theta. Can't forget the d theta. Well, what is this going to be? When I evaluate this limit, as t approaches infinity, e divided by infinity is going to be 0 minus 1. So I'm going to have negative 1/2, the integral from 0 to 2 pi of 0 minus 1 d theta. Okay, and I'm going to get a negative 1 there, which is just going to make this become a positive 1/2. 1 d theta is going to integrate just to theta, and to finish the calculation, I have 2 pi minus 0, or pi. Don't forget, this was a squared is pi. So if a squared is pi, then the bounded area under the curve is the square root of pi. So my answer, the integral from negative infinity to infinity of e to the negative x squared dx, or the area bounded by the bell curve e to the negative x squared, and the x-axis is equal to the square root of pi units squared. And there you have it. El Clásico, not El Clásico in the La Liga sense of Barcelona and Real Madrid, but El Clásico double integral in polar coordinates.